Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering the question of the longest string chain. This is one of those questions that is very difficult when you're just starting out, or if you've only done a few algorithm questions. It's especially difficult if you haven't done that many dynamic programming questions. But it's also one of those questions that becomes surprisingly almost easy once you have done a lot of dynamic programming questions and once you have started to really ingrain those patterns of memoization and caching in your mind. So I gave a lot of hints as to how we're going to be doing this question or solving it. But with that, let's actually look at what it's asking us and then dive into the conceptual overview. This question gives you a list of arbitrary strings, like the strings that I've got in front of me here, written in white. And the question wants you to return, or to write a function rather, that returns the longest string chain that can be made from these input strings. Now, a string chain is going to be defined as follows. Imagine you have two strings. Let's say you've got, A, B, C, and let's say that you've got A, B. And both of these strings are in your input list. The fact that you can remove one letter from ABC, in this case C, and that by removing this letter you obtain the word AB, or the string AB, which is also in our list of input strings, these two strings now constitute a string chain of length 2. Now similarly, you could remove, let's say, the letter B, and you would have AC, and if we had the string AC in our list, then these two strings would constitute a string chain of length 2. Okay? Now, we want to find the longest string chain that we can form from all of these input strings. So this problem, at first glance, is actually very difficult. Like I said before, especially if you haven't done a lot of other problems, because you quickly realize that you're gonna need to sort of try removing every single letter from every string to see what happens. Like, do you find a string that's still contained in your list of strings? You're gonna have to do something like that. But that's pretty computationally demanding, right? Removing letters from strings is not, trivial. It takes time complexity, for instance. And then you start to quickly realize that if you don't optimize your algorithm in some way, shape, or form, you're going to have a really terrible algorithm. As an example, imagine you had the string, A, B, C, D, E, F, which I think we do have in our input list here. You can imagine that you would try removing every single letter from this string. So you might start by trying to remove the letter A, right? Or then you might remove the letter B, right? So you would do that for every letter. And then let's assume that this string now, A, C, D, E, F, is in your list of input strings. Well, then you would try removing every single letter from this string. So you would try removing every letter from A. You would try removing A, and you would only have C, D, E, F left. Or you would try removing C, and you would have A, D, E, F left. And you would keep doing that, and you can imagine that if you have to do this for every single string in the array, like for every single string in the array, you have to try removing stuff, and then redo the same sort of logic for every other string in the array, you're going to end up with like a monster algorithm as far as time complexity is concerned. So, this is when you start to realize that the simplest way, or rather the key to sort of cracking this particular algorithm and this particular question, is to realize that every single string in the array has a longest string chain where that particular string is the largest string. That's the first thing to realize. So I'll repeat this, and let me erase this here. Every single string in the array of input strings has one longest string chain for which it is the largest string. So for instance, ABDE has some longest string chain where it is the longest string, meaning it is at the head of the chain. Same for ABC, same for ABD, same for ABCD, and etc. And the second thing to realize is that you should only ever compute the longest string chain for each of the input strings once. Not twice, not 3 times. You should never do duplicate computations. You should only compute these the longest string chains for each of the strings once. And once you realize that, and once you then realize that by computing them once, you can sort of build off of them to compute the string chains of larger strings, then this algorithm becomes almost trivial. So if you're starting to get an idea of what I'm hinting at here, great. If you're not, if you're super confused, also great, because hopefully I'm about to demystify what I'm saying. So I think the best way to actually demonstrate this, or to explain this more clearly, and the best way to solve this problem, to be honest, is to do so in a very intuitive way, and to make it as intuitive as possible, I'm actually going to sort our input list of strings. So this example here, I'm going to sort the strings by their length from the smallest string to the largest one. So I'm going to take a second right now to do this. So if I select AE, that would be the, I guess I'll select the comma as well. AE would come first. AE stands for Algo Expert, by the way. ABC, then ABD, then ADE, then ABDE. Is there another? No, there are no other 4-letter words. ABCDE, 1 ABDE, and then finally, let me move this back up here. Okay, so we have now sorted our input list of strings from the shortest string to the largest one, or the longest one. So now, what we can do, if we go off of the 2 sort of key things that I said to realize in this problem, is we can iterate through these strings from left to right, meaning from shortest to longest. And at every string, we compute the longest string chain at that string. So we're going to try removing letters and seeing if the leftover strings are part of our input strings and so on and so forth. But because we have sorted these strings by length, we can intuitively, very intuitively, realize that, hey, if we come across a string at one point when we remove a letter that is in our input list of strings, we will have already computed that string's longest string chain because we are going from shortest to longest, right? And we can use that to avoid doing a bunch of unnecessary computations. So once again here, I'm doing a lot of talking, so let's actually go through this example in case it isn't clear. So we start with the shortest string, AE. Now, in practice, we could actually skip this string because if it's the shortest one, there's certainly nothing that could come before it in a string chain. But, we don't really need to take care of this edge case. It's not going to optimize our algorithm from a space-time complexity analysis point of view, so we're just going to go with it. We start by removing every letter from the string to see if the resulting strings are contained in our list of strings. So we're going to say, okay, let's remove the letter A. So we have only the string E. Is E in our input list of string, or of strings, plural? Now, as a side note here, you can imagine that we can dump all of these strings in a hash table to make this lookup constant time. And we're going to do that. In fact, we're going to have a specialized hash table, which I'll get into in a second, but we're definitely going to be dumping the strings in a hash table so that we can look up if any given string is inside the list of input strings in constant time. So is E in here? No, it's not. Okay, throw it out. Now remove the letter E from AE, and you're left with A. Is A in our list of strings? Again, we look it up in a hash table. No, it's not. Okay, throw it out. So right now what we can say is that for the string AE, I'm going to put like an arrow here. We have a longest string chain of length 1. Now the prompt tells us that there isn't really such a thing as a string chain of length 1. String chains have to have minimum length 2. So basically, there is no string chain starting at AE. So the next string in the chain starting at AE is the empty string. So I'll write that with 2 quotes. And the longest chain length starting at AE is basically 1. Or again, you could put like 0 or -1 or whatever you want to call it. I'll put 1 here because basically there's just one word. Okay, so as a little hint here also, I mentioned that we would have a specialized hash table. What we're going to do is, instead of dumping all of these strings in a hash table that just maps them to true or something, we're going to have every string map to the specialized object that is going to have the next string in the chain. In this case, it's going to be the empty string for AE, and the longest, or the length of the longest string chain starting at that string. In this case, it's going to be 1. I'm not going to actually write this hash table here in the conceptual overview, but I'm storing the values, or I'm writing the values stored in that hash table right here with this arrow pointing to these values, okay? This will make a bit more sense in the code, but hopefully you're following along here. Okay, so now we move on to the next string, ABC, and we start to remove every single letter from this string to see if we have a resulting substring or smaller string contained in our list. So ABC. Start by removing A, and we are left with BC. BC is not in here. And again, we're doing constant time lookups. This is the last time I'll say it, but we're doing constant time lookups in our hash table. BC is not here. Okay, try removing B. Now we have AC. AC is not here. Okay, try removing C. We have AB. AB is not here. We're going to erase this, and we're going to say, okay, ABC, the longest string chain that starts with ABC, is of length 1, and the next string after ABC is the empty string because there is no string after ABC. Great. Move on to the next string. Now we have ABD. Try removing the first letter, D. So we have AB. Is AB in our list? No, it's not. Okay. Try removing the second letter, B. Is AD in our list? No, it's not. Try removing the third letter, D. Is AB in our list? No, it's not. Okay. Same thing. So far, pretty simple. This now points to the empty string and 1, because the longest string chain starting at ABD has length 1, and the next string in this chain is the empty string because there is no next string. Now we move on to ADE. Try removing the A, DE, not in our list. Try removing the D, AE. Oh, wait a second. AE is in our list. We have AE right here. So now what can we do? We can say, well, wait a second. AE points to a chain of length 1. Because, even though we said that the prompt doesn't define a chain of length 1 as a real chain, point is, there's one word starting at the chain at AE. I realize I'm contradicting myself a little bit with the way the prompt is worded, but that doesn't really matter. Point is, in this chain here, there's one word. Okay, well, wait a second. There's a one word here. AE is in our hash table and in our list. So therefore, ADE is part of a string chain that points to what's the next word after ADE? It's AE. And it's a string chain of length 2. 1 plus 1. Why 1 plus 1? Well, because AE was a string chain of length 1. And we add 1 because we now have a new word, ADE. So 1 plus 1, 2. Awesome. Okay, so now we can keep going and you can start seeing that, well, wait a second. If we ever find the string ADE, we will be able to, we will know that we have a string chain at ADE pre-computed of length 2. So, okay, now we were at AE. This was when we removed the letter D from ADE. Now let's move on and remove the letter E from ADE. So now we have AD. This isn't in our list of strings, so we skip. Now we go to ABDE. So we try removing every letter. So if you remove A, you have BDE. BDE is not in our strings, so we skip. Try removing the letter B, and now suddenly you have ADE, and what do you know? ADE is in our list. ADE is right here. It's the word that we just went through. Now the key thing, I guess I forgot to mention that when we were at the AE earlier, the key thing here is that once we find ADE, and we know that ADE is on our list, because we have sorted the words or the strings earlier from smallest or shortest to longest, we know for a fact, we don't need to do any sort of check or any sort of weird computation. We know for a fact that ADE has been pre-computed. And that's super important. And that's why I think that this sorting here, the fact that we sorted these words or these strings, makes this problem a lot more intuitive. Because as I'll show you a little bit later, probably during the code walkthrough, you don't actually need to sort these words or these strings, but by sorting them, you just make the problem so much easier to grasp. And this is something that I would even bring up to your interviewer if you are given this problem. Explain that by sorting it, you make this problem a lot more intuitive, and you prevent or you make yourself not have to do annoying checks in your code later on. Because you can imagine that if you hadn't sorted them, it's possible that ADE would have come after ABDE. And so if you got here to ADE, you would say, oh, ADE is in our list of strings, but we haven't computed its longest string chain, and you would have to make a check to know if you've computed it already. So now we have to compute it. And it just adds a little bit of complication to the algorithm. Now, of course, the sorting of the words does affect time complexity, but you'll see at the end that it doesn't affect it that much. Okay, so ADE. ADE is in here. We know that ADE has a string chain of length 2. So ABDE can be added to the string chain. So we can do 2 plus 1. Again, the 2 comes from the string chain at ADE. The 1 comes from the fact that we're adding a word, ABDE. So ABDE now points to ADE and points to 3. Right? We've got a string chain of length 3, where the first string is ABDE, and the second string is ADE. Now we try removing the next letter, which is the letter D. So we have ABE is the word Abe in our list. No, it's not. So erase it. We move on to the next letter, the letter E. Remove the letter E, so we now have ABD. And here we find ourselves in an interesting spot. ABD is in our list of strings. But so what we have to do now, because we already have a string chain at ABD, we've already stored AD, the next string is ADE and a string chain of length 3. We should see, well, is this string chain better by any chance? The one that points to ABD instead of ADE. And so we compare. ABD has a longest string chain of length 1. So 1 plus 1 equals 2. 2 is smaller than 3. Therefore, the current string chain that we have at ABD that points to AD is better than the one that would point to ABD, because 2 is smaller than 3, and we want the longest string chain. So we can skip this. And now we're done with this string. So now at this point, I think that you're really starting to understand how the algorithm works. I'm going to still finish the example, but I'll go much faster. And then we'll dive into the final parts of the algorithm. So A, B, C, D, E. Remove every letter. B, C, D, E. We've removed A. That is not a string in our thing. Then we have A, C, D, E. That is not a string in our list. Then you have A, B, D, E. That is a string in our list. That is this one. So great. We will now point to A, B, D, E. A, B, C, D, E will now point to A, B, D, E, which will now have a longest string chain of length 4, which is 3 plus 1. Then we have A, B, D, E. Or wait, I just did that. No, then we have A, B, C, E. A, B, C, E. This is not in our list. And then finally we have A, B, C, D. This is also not in our list, so we skip it. Then we get to the second to last string, 1ABD. So 1ABD, we remove 1, and we are left with ABD, or ABDE, sorry. ABDE. This points to the same thing. So here we're going to put, we're actually going to grab this and say, okay, you can put ABDE here and have this point to that. And that's also a string chain of length 4. And then I'm going to skip removing all the other letters because you can clearly see that no other string in our list has the number 1 in it. So you know that for the string 1ABDE, this is the best string chain that we can make. And then finally, as you can clearly see, ABCDF, or ABCDEF, will have a string chain where you remove the F, and that points to ABCDE. So I'll put an arrow, ABCDE, and this would point to length 5. And so now we have clearly found the longest string chain that starts with ABCDF. You can imagine that we're going to write one more function in our algorithm probably that builds up the string chain. So we would traverse this entire list, find the string that points to the longest string chain. Keep in mind, it might not be the longest string, right? Maybe it's a string in the middle that has a shorter length that points to the maximum string chain. It doesn't really matter how large the first string is. Here it happens to be the final one, the longest one. But so we know that this is the longest one, and we can construct the string chain by just traversing all of the next strings that we're pointing to. So we start with ABCDF, which we put up here as the first value in the answer. This points to ABCDE. Add that here. ABCDE points to ABD. Add that here. ABD points to AD. Add that here, and so on and so forth. So as you can see, we've started here, go here, 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 here. And then I guess here, and then we're done. So that's how we built our longest string chain. Let me undo this. At this point, we can dive into the complexity analysis portion before we jump into the code walkthrough. As far as time complexity, this algorithm is going to run in, so n, or sorry, let's do a large N, where n is the length of the input list. Why n? Because we're going to be iterating through all of the strings once, at least when we dump them in the hash table, but then we're going to reiterate through all of them as we did throughout the example here, and then we're going to try removing letters from them and so on and so forth. When we build our longest string chain, we're going to be iterating through the strings, and we might have a longest string chain of length n. Point is, clearly there's going to be an n here. Now, it's going to be n multiplied by m squared, where m is the length of the longest string, so in this case, A, B, C, D, E, F. Why do we have this m squared? Well, think about it. We iterate through every string at one point, and for every string, we iterate through that string and remove every letter. So when we iterate through all of the letters in A, B, C, D, E, F, that's O of m, and because A, B, C, D, E, F is the longest string in this entire array, we have to assume the worst case where they all are of length m, so hence O of m. But then when we're creating a new string, right, when you remove a letter and you create a new string without that letter, you are iterating through the entire string to rebuild it, at least in most languages, right? Python, JavaScript, Java, Golang, you're going to be doing that. So that's another m. So O of m squared. And this will probably be more visible in the code because you'll see like the actual for loops and so on and so forth. And then finally, there's also an n log n that we have to add, n log n, for the sorting at the beginning. Now again, I want to make it clear here that, yeah, we sorted the strings by their length. So we have this n log n. So we did add to the complexity analysis, or to the time complexity. But this made the algorithm so much more intuitive. It made the code cleaner, because we don't have to do that weird check of like, oh, if we get to ADE, have we already computed the string chain of ADE or have we not computed it? And in practice, this is something you could tell to your interviewer, the log of n, unless we're dealing with a tiny m, unless we're dealing with tiny strings, it's very likely that log of n will be smaller than m squared, right? And if log of n is smaller than m squared, then this n log n is sort of worthless. It doesn't affect the algorithm. So granted, like this, I do want to make it clear, yes, we are affecting the time complexity, but in most cases, it's just going to be fine because it's actually not going to affect the time complexity, like it's going to be swallowed by the m squared. Or if it isn't swallowed by the m squared, then we just had a much more intuitive algorithm that is going to be slightly easier to code out. So this is something to tell your interviewers. Finally, as far as space complexity, we are going to have O of nm space. The reason we have nm is pretty simple. We are storing a hash table of n strings, where each string potentially points to another string of potentially at most length m, hence n times m, right? All the strings that we point to. Similarly, we are building a string chain that will have length at most n, where the strings in the string chain will be potentially starting at a string of length m all the way to a string of length 1, and that converges to nm. So our space complexity is going to be O of nm. So that's it for this question, or for the conceptual overview of the question. Now let's dive into the code walkthrough to see what it looks like. All right, so we've got our longest string chain function defined. It takes in a list of strings. And the first thing that we're going to want to do is to dump every single string in a hash table, where every string is going to map to an object or a dictionary in Python containing two properties. The first one is going to be the next string in the longest string chain starting at the given string. And the second property is going to be the actual length of that longest string chain. So that was a mouthful. Let's actually type the code for this so that we can see what we're talking about. We're going to declare our string chains, which is going to be our hash table. It's going to be initialized to be an empty object or an empty dictionary in Python. And for every string in our list of strings, we are going to say string chains at index string, or at the given string. It's going to map to an object or a dictionary, mapping next string to the empty string at first, and max chain length, or longest chain length, whatever you want to call it, to 1. Because every string is theoretically part of a string chain of length 1, even though the prompt tells us that that is not actually a string chain. Okay, cool. So that is our initialization step. That's sort of the very easy step. The second thing we're going to do is make the problem more intuitive and more easy to deal with by sorting all of the strings based on their length. So we'll say sorted strings is going to be equal to sorted strings equals length. So here, however you want to do it in your programming language of choice, just sort these strings based on their length. And then, now we get into the crux of the algorithm. For every string in this list of sorted strings, so here we want to start with the shortest string and go to the longest, we are going to try removing all of their letters and try to find basically each of the string's respective longest string chains starting at them. So for this, we're going to probably abstract this logic out into a different method. So I'll call this find longest string chain at the given string. And we will, of course, pass our string chains hash table, because that's going to be what sort of allows us to compute everything really easily. And then for now, I'll pass, because I think we're going to have one more step here at the end of the main function. But for now, let's write this method out. So finding the longest chain takes in a string and the hash table. And what do we want to do? Well, we want to iterate through the given string. So here, like we said, we're passing in an actual string here, right? So we're dealing with a single string. Iterate through the string, through every letter. So for I in range len of string, right? Iterate through every letter. Try removing a letter and seeing if the remaining string when you remove that letter is in our string chain. So what we'll do here, we'll also abstract this logic out, even though, removing a letter and creating a new string is probably a one-liner. Let's actually abstract this out. So we'll say smaller string equals get smaller string, and we'll pass in the string and the index of the letter that we want to remove, so index I. And I'll pass for now and quickly define this method. So get smaller string takes in a string and an index, and it should be very easy, right? We return the string starting at index 0 and going all the way to index. So we slice the string from 0 to index, and this is always excluded in Python, plus the string starting at index plus 1 and going all the way to the end, right? So we want to remove basically the letter at the index, if that makes sense. So that is our get smaller string method. We call it here, we get the smaller string, and let's remove this pass, if the smaller string is not in string chains, then we can just continue. Otherwise, we can try to update the longest string chain. And the reason I'm going to abstract this out into another method, which I'm going to call try update longest string chain, is because if you remember, there was one example, I think, or maybe there were two in the conceptual overview, where we already had computed and stored a string chain in our hash table for a given word, and we found another potential one, and we needed to compare which one was the longest one. And that's a sort of piece of logic that we can abstract out yet again in another method. So try update longest string chain. We'll pass in a string. We'll pass in the smaller string, and we'll pass in our hash tables, or a hash table, sorry. And that should be it, right? For this method, that should be it. We iterate through all the letters, get every smaller string. If our smaller string is not in our hash table, just continue. To be honest, we don't even need this continue. We could put this in here and not put the not here. Anyway, so now let's write the try update longer string method, or longest string chain method. Try update longest string chain. It takes in, let's say, a current string. It takes in a smaller string, and it takes in string chains. So here we are going to say the smaller string chain length. I'm going to declare a bunch of variables to make this a little bit more easy to fit in a certain line. So the smaller string chain length is going to be equal to string chains at smaller string and max chain length. Then here we're going to do current string chain length is going to be equal to string chains at current string at max chain length. So we know what the string chain length is of the smaller string. We know what the current string chain length is for a current string. It might be 1 right now, or it might be something that we've already found, like, earlier, I think in the conceptual overview when we were at, A, B, C, D, E or something, it was 3, I think, or 4. And then we say, hey, if the smaller string chain length, let me give myself a bit more space if the smaller string chain length plus 1, because we add the current string, is greater than the current string chain length, then we want to update it. Then we have found a better string chain. So we're going to say string chains at current string at max chain length is going to be equal to this computation. And then we can say the next string is going to be equal to the smaller string. Right? So this method, what it says is, again, this is very simple. Just constant time checks. It says, hey, whatever string chain length we have at our smaller string, if we add 1 to that, is that better than what we currently have at our current string's longest chain? If yes, then let's update it. Update our current string to have that new length and to point to the smaller string as the next string. And that's it. Now we're almost done. Like, now we've done the entire logic of creating these string chains. All we need to do now is finally build the longest string chain. So we can say return build longest string chain. And this is actually similar to a lot of other dynamic programming algorithms that we have on AlgoExpert, where you end up having an additional step at the very end to build whatever the answer is. Typically, this final step doesn't really add anything to the complexity analysis of the algorithm. You've done all the tough part. You just need to sort of backtrack your way to create the answer. But so we'll pass in the strings and we'll pass in the string chains. And so if we define this, define build longest string chain, it takes in strings and string chains. So let's see, what do we want to do here? We want to, we've stored in our hash table a bunch of objects that have all of the longest string chains starting with each string. We want to find the longest one of those. It's not necessarily the one at the longest string. It could be somewhere in the middle of the array. So we need to find that first, and from there we can backtrack our way and create the longest string chain. So we'll say max chain length equals 0, chain starting string equals, let's say, the empty string. And then we'll iterate through all of our string. For string in strings, we check if the string chains at the current string, if that max chain length is greater than whatever we've stored here. And if it is, then we update the max chain length to be equal to this. And we update the chain starting string to be equal to the string. This entire logic here is just, a for loop through the strings and just small checks to find the first string in the largest string chain, this one. And once we've found this, we can actually build our chain. So we can say longest string chain is going to be equal to an empty list. Or actually, this is the name of our function. So let's call it our longest string chain. And we are going to do current string equals chain starting string while our current string, while our current string is not equal to, what is our base case? Our base case is when we are at the empty string. Here we have found the end of a string chain. So while our current string is not equal to the empty string, we append to our longest string chain, we append the current string, and then we set the current string to be equal to string chains at the current string at the next string, right? So we're backtracking our way and building this entire string chain. Hopefully that makes sense, right? This is pretty straightforward. You say start at the first string, the longest string in our longest string chain, and keep traversing through the next strings until we reach an empty string. And at the end, we can return the longest string chain. I suppose the prompt does tell us that we have to return an empty list if there are no string chains. And again, words or strings of length, chains of length 1 are not actual chains. So we'll do a ternary here, return empty array if len of our longest string chain equals 1, else our longest string chain. And that's it. This is our algorithm. So it's a lot of code. It's non-trivial to write out, but I do think that it is quite simple and quite, I would go so far as to say quite beautiful once you get that whole like dynamic programming pattern and caching or memoization pattern into place by computing these values and storing them in this hash table. And notice also that because we just build up our string chain at the very end, we don't need to store n string chains, because that would have been another way to do poorly in this problem. Would have been, imagine we stored every single string chain at every string. No, we don't need to do that. We can just store the last or the next string in the string chain. So this algorithm is going to run in, what did we say, O of n times m squared plus n log n time. And it's going to run in O of nm space, where n is the length of the strings, or the number of strings, and m is the length of the longest string. So very quickly we can see here we're iterating through n strings. That's going to be O of n, and we do sort of constant time operation here, nothing fancy. Then we sort the strings by their length, so that is where the n log n comes from. And again, this is purely done for intuition and to make this algorithm a little bit cleaner and the code a little bit cleaner. But refer to the conceptual overview if you aren't sure why we're sorting. Like I said, it's not entirely necessary, but I do think that it makes the algorithm nicer. So I'm going to keep it that way. Perhaps I'll leave it up to the viewer to try to re-implement this problem without the sorting, just to see if you can actually get it to work. Then we iterate through all of the strings again in the sorted strings, so that's another O of n. For each of the strings, we find the longest string chain. So here we iterate for each of the strings through all of their letters. That's one of the m's here. You imagine that the longest string is going to have length m, so that's 1 O of m. And for each letter, you get the smaller string, where you have to slice the string and remove, the letter at the index. So that's another m, right? That is nested. This get smaller string method is nested inside a for loop of length m, and this takes O of m time, so O of m times O of m squared. This is a constant time check. We try to update the longest string chain. These are just constant time checks, right? We're just like comparing values and updating values, so very simple here. So now we have gotten O of n times m squared, because remember the m squared thing is nested in this for loop of O of n here. We know the n log n from the sorting, and then finally build longest string chain. What do we do here? We iterate once through all the strings, that's just O of n, and do a couple of comparisons. And then we backtrack through all the strings, or through the string chain, which is going to be at most length O of n, or at most length n, sorry. So this doesn't affect the space or the time complexity. And space complexity, nm, because we are creating this hash table as well as our longest string chain array. And these are going to have, length n, or at most n, and we're going to have strings of at most length m inside of them. Here we'll be pointing to strings in the next string of length at most m. Our array is going to have strings of length at most m, so therefore n multiplied by m space. So that's it for the algorithm. Let me backspace all of this here. That's it for the algorithm. I hope that you found this video informative. I hope that you enjoyed this algorithm. I'm very curious. I'll probably never be able to hear you tell me this, but I'm very curious if you agree that this algorithm is actually a lot easier than it seems once you see the solution. I don't know why, because I remember I struggled a lot with this problem way back when I first saw it, when I hadn't really ever prepared for algorithms and all that. But now it almost seems, surprisingly like elegant to me and surprisingly easy to do. So I'm very curious to know if you find it that way too. Either way, I hope this video was informative, and I will see you in in the next one.